All right, hello pre-cal. This is lesson 9.6, equations of asymptotes. We're going to be doing a bunch of different things here. This is kind of like a giant review, and you will need your calculator. So whether you have your calculator handy, your graphing calculator, or having desmos.com open in another tab is definitely something useful you're going to need. So keep those things close by. So first here we just have some, again, using function notation. I just can't stress function notation enough, right? So generic function notation just says we have some output is whatever generic f function we've got going on here. So here I have a generic function f, and when we write this stuff, normally you can see that that 5 is in place of the x. So this is asking you, hey, what's the output when you have an input of 5? So we go to 5 on the x-axis, and hey, what's the output? And it looks like there could be two choices. So which is the actual choice? 2 is the correct answer. This point is an open circle. It means it's not included. Not, that says not, I swear. And this is the actual value that is included, the actual output. All right. Now, we normally see it written y equals f of x, but you can always flip around an equation. And so sometimes it's written f of x equals y. And I kind of like this way better because now you see that the x and the y really just represent an ordered pair on your function. And that's something good to remember. So here I have, again, my function, generic function f. Looks like it's probably an absolute value function. And we want to find the x values where f of x is equal to 0. So again, what they're saying is, hey, we have an ordered pair that is some x, but a 0 for the y. So where is the y-axis equal to 0? Anywhere on the x-axis. So when they say where does the function equal 0, these are the zeros where the graph crosses the x-axis. And that's why they're called zeros. Old school notation is roots. And so we see that we have zeros when x equals -1 and when x equals 3. And I think you can just type in -1, 3, and it'll do the whole set notation stuff in Delta Math, I think. But this is asking where does the function equal 0? We can also say stuff like, hey, where does the function equal 3? Where does the function equal 3? Well, here's where the y value is 3. So anywhere where the graph crosses that line, right here, you get a y coordinate of 3. So when x equals -4 and when x equals 6, you get y coordinates of 3. Kind of interesting. So that's a good thing to know. We can also do it using the calculator, which we're going to do in just a couple minutes. Find the vertical and horizontal asymptotes. This is really important. And when you do it enough, like I can look at this function and know what the vertical and horizontal asymptotes are. But when in doubt, you can graph it out. So you can always go use your calculator and double check, and I would say graph it. And for us right now, I think that's okay. Had we been in person, no, you would know how to do this. we glossed over this, though, this year. So first of all, vertical asymptotes always come from a denominator. All right, so that's one thing you absolutely want to know. Vertical asymptotes always come from a denominator. So in this function, my denominator is 2x plus 8. And what we do is we would set that equal to 0 and solve for x. And that's going to give you your vertical asymptote. So 2x equals -4. I'm sorry, -8. And then divide by 2 and we get -4. And any vertical asymptote always needs to be, it is an equation of a line, so you do need the x equals. And that is the equation of a vertical line. On this rational fractional function, this outside number is actually taking the horizontal asymptote and sliding it down too. So this little number on the outside actually happens to be the horizontal asymptote, y equals -2. Now, I don't necessarily think you know that yourself, so I'm going to show you. When in doubt, graph it out is my favorite saying. Now, when you're putting something like this function in your calculator, you need to do it very carefully. And for those of you going on to calculus, you have to know how to do this on your calculator. You don't get to use desmos.com. So you have to know. All right, so on the calculatora, whoops. Okay. I'm going to my y equals graphing menu. And when you have a rational function, you actually have to make sure that you get parentheses around. I always say it's a good idea to put parentheses around the numerator and parentheses around the denominator. It's just a safe bet. You'll get it right if you do that. Now, -2 is just subtracting 2 on the outside of the function. We don't need parentheses around that. So I'm going to just do a zoom standard. And so let's look at our graph and see what we see. So on this graph, this is a typical rational function, these little sort of inverted L type shapes. Where they diverge, one goes to positive infinity and one goes to negative infinity, that is a vertical asymptote. And you can see it right there, 1, 2, 3, -4. So it does appear like we verified. We get that vertical asymptote. Sometimes it's good to make a little sketch here. It looks like there's definitely a vertical asymptote at -4. And then you can see where we grow for large values of x, we sort of are leveling off here. And for negative values of x, we are sort of leveling off. So that's a horizontal asymptote where things level off. And you can see that that looks to be about at -2 on the y-axis. So, and then we get these little functions, these little L shapes. And so it's good to be able to recognize what's happening in a graph to verify what you're thinking, right? So that's a good way to do it. What's your guess? All right, here we have a rational fractional function, but you'll notice it's not a constant on top. Instead, it has the same degree. And when they have that same degree, when the degrees match, all you have to do is reduce those coefficients. So that's kind of a cool thing. And then if we wanted to find the vertical asymptotes come from the denominator. So we would say 7x plus 21 gets set equal to 0. We would subtract 21 and divide by 7, which is -3, which I'll just write. There we go. So there's our vertical asymptote and horizontal asymptote. And again, I can double check. Always a good idea. When in doubt, graph it out. 2x minus 5 in the numerator. And then 7x plus 21. Whoops, not 12. How about 21? There we go. And the denominator. And again, I put parentheses around my numerator and denominator when I'm using my calculator, just to make sure I do it correctly. Now, 2/7 is very difficult to see, but it's, between 0 and 1, so we're pretty close. That seems about right. And then -3, -1, -2, -3. When you trace and type in -3, what will you expect to see? Exactly nothing. It's y equals blank because it's undefined. There is nothing there. It's undefined. It's not definable. All right. If it was defined, a number would be there, like 7. But it's undefined, meaning we can't define it. It's not possible. Took me a while to figure that out. So. Let's look at this graph. This is an exponential function. Exponential functions, those are Superman graphs normally. They grow quickly, but this has a negative in front, so it's actually getting reflected. So it's actually going to negative infinity. It's growing to negative infinity very quickly. But exponential functions have a horizontal asymptote, always, always. And in this case, that horizontal asymptote is at y equals 0 because there's nothing added or subtracted. And again, if we wanted to be sure, negative 2.1 to the x. When in doubt, graph it out. And you can see there's our exponential. Now, the question is, does it stop right here? No. The calculator just says, your pixels are too big and I can't graph you anymore, because then it'd just be graphing a horizontal line, which I can't do. So it has to stop. But you'll notice if you go to the table, so on the Casio, you press menu and go to table. But here we just do second table. You can go, and we keep getting outputs. Look at, they're just getting smaller. And that's what this is, negative 3e to the negative 4. That's scientific notation. That's negative 3 times 10 to the negative 4th power. So a very teeny tiny number. It moves the decimal place 4 places to the left. And you can see it's just getting smaller and smaller and smaller and smaller. So we're just getting closer and closer to 0. We're never going to quite get there. These are just getting really small numbers, like 0, 0, 0, 0, 0, 0, 0, 0, 0, 9. There we go. That's the number. Okay. All right. So there you go. You can see it's just leveling off here, approaching 0. There is no vertical asymptote. This graph goes forever to the left and it goes forever to the right. I can plug in any x value I want. So there is no vertical asymptote here. Now this one is actually a calculus question, which is very cool. And so we're going to just approach this by graphing it. In calculus, we actually talk about the actual definition of a horizontal asymptote, but we just sort of go with it in pre-cal at this level. So again, we're going to graph this, and I'm going to make sure I put my numerator in parentheses. So 2x minus 6 divided by the square root of. On the Casio, you need to put parentheses around this stuff underneath, but here I have pretty print. X squared minus 4x minus 32, all under the radical. And let's look at this. This is a really interesting graph. All right. So the question is, what are the vertical asymptotes and what are the horizontal asymptotes? So we have this big old gap here. There's like a little L shape here, and there's a wee little L shape here. Okay. And so it looks like the graphs are going in this way. This is kind of interesting, right? Really interesting looking. And so what is happening here? Well, horizontal asymptote, it looks like it's starting to level off here. So maybe that's about at -2. That's interesting. Okay. I don't have enough graph. I'm going to change my window. I'm going to make my x-axis longer. I'm actually going to make both axes a little bigger. So I'm going to go, let's go -30 to +30 in the x direction, and -30 to +30 in the y direction, just so we can see a little bit more clearly. Oh, look at that. It kind of, it doesn't seem to go on forever. It terminates. That's interesting. I'm curious where it seems to stop here. I want to try and figure that out. Okay, but it does look like we've definitely got some horizontal asymptotes going. And it looks like, I'm guessing this one here might be at -2, and this one here might be at like +2, which is kind of interesting. So let's talk about that. The horizontal asymptote always comes from the leading coefficients here. So what's going on? We have 2x over the square root of x squared. Well, the square root of x squared is x, but actually it's the absolute value of x, and that's something that Delta Math glossed over this year. But if I put a number in here, like -5, I would have to square it. So it becomes positive 25. And then when you take the square root, it's positive 5. But I started with a -5. It always comes out positive. And what happens here then is you have a number like x, and let's say we plug in -7 for x. Well, 2 times -7 would give me -14 in the numerator. But in the denominator, the absolute value of -7, well, that's just 7. So we actually end up getting -2. So it's kind of interesting. So what happens when x is less than 0, so when we have negative values of x, the horizontal asymptote is going to end up being -2. So you could try again. You could plug in -8 and see what happens. You'd get -16 over 8, which still gets you -2. You could plug in -9 for x, and so you'd get -18 over +9. So anytime your x value is less than 0, you would get y equals -2, and that's what we're seeing here. For x values less than 0, we're getting -2 for the horizontal asymptote. But for x values greater than 0, that horizontal asymptote, let's see, for numbers greater than 0, we're talking about positive values. So what happens when we stick in a positive number like 10? If we plug in 10, we would get 20 over 10. We would get +2. So this x can change sign, positive or negative, but this one's always positive. So we have 2 different answers here, and that's really interesting. So there are 2 horizontal asymptotes, and that's why they're different. That's what absolute value does. It just creates 2 answers, right? Every time we had absolute value, plus or minus, there were 2 equations. Okay, so what's going on in the middle? In the middle, I don't actually think we have vertical asymptotes. Because what's happening is to get vertical asymptotes, let's look and see what happens here. Vertical asymptotes occur when the denominator is set equal to 0. But because this is under a square root, it also has to be greater than 0. Do I want to do it this way? All right. So we could solve this, and if we solve that, that's going to give us potentially vertical asymptotes. So let's see. So we would square both sides to cancel out the radical. So we have x squared minus 4x minus 32 has to be greater than or equal to 0. Nope, you know what? We don't have to do this. I think we can just say to find a vertical asymptote, we set our denominator equal to 0 and solve. That's all we have to do here. So x squared minus 4x minus 32 equals 0. We can double bubble. X times x is x squared. Let's see, -8 and +4 give me my 32. So we get vertical asymptotes at x equals 8 and x equals -4. I think this is really tough. I'm going to have to double check. So I'm going to take a second to do that. I did check. So at -4, it is I did trace. So I did trace -4, and it is undefined. Normally, for a square root function, there would be a value there. So I do believe that there is a vertical asymptote here. So it does get infinitely close to this, and the calculator has just stopped drawing. And the other one would be at 8. So let's do trace 8. And again, it's undefined. So I do believe there's a vertical asymptote. I'm going to take a second and figure that out, though. All right, so I did just check, and it is correct. To find vertical asymptotes, we just need to set the denominator equal to 0 and solve. So that simplifies things really nicely. So that's good. These are the vertical asymptotes, and you do have to type in the full equation. So there are 2 vertical asymptotes here. On Delta Math, their graphing engine is so much better, so you can actually see what it looks like, which is a lot different than what your calculator spits out. Desmos.com also is going to have a way better graph. So check Desmos and have a look at the graph, and I bet you'll see that it does continue on. It doesn't just terminate. All right, last thing here is all calculator work. And for this, we want to figure out the solutions where f of x is equal to g of x. So what are we doing? We are doing f of x, here's f of x, is equal to g of x. Here's g of x. So if I'm going to set f of x equal to g of x, well, let's see. What is f of x? Well, there it is right there. So we would write 0.15x cubed plus 2.1x squared plus 6x minus 1.7 is equal to, what's g of x? Absolute value, 1.5x minus 6.6. And we are going to use your calculator because that's what this is. This is an exercise of, can you use your calculator? We are putting the left-hand side in y1 and the right-hand side in y2. Now, if you use Desmos, you can just type in one equation in one line and in another line type in the other equation, and we're just looking for where they intersect. So that's what we're going to do. We're going to find the intersections. It is just a system of equations, which we've been working on, right? So this all goes together, ladies and gentlemen. And I do have a reason for doing stuff. All right, so let's see. So 0.15x to the third power plus 2.1x squared plus 6x minus 1.7. And then in my second one, absolute value. Absolute value on the TI is under the math menu. So we're going to do math and then arrow to num. On the Casio, you're going to press option and I think more, and then find num and ABS. And again, you'll want to use parentheses. So 1.5x, and then the outside minus 6.6. And I can't find my Casio calculator anymore, so we'll see. So this is a cubic. So this is this sort of roller coaster shape, stretchy S. Absolute value V is what we've got there. And you can see we've got a couple, 1, 2, 3 points of intersection. On the Casio, it's super easy. You do G solve, so shift G solve, and then isect. And it'll give you the leftmost intersection, and then you arrow to the right, and it'll give you the next intersection, and you arrow to the right, and it'll give you the third intersection. On the TI, it sucks. Oh, wrong thing. Wrong thing. Okay. We want to calculate. So we have to do second calculate the intersection. And I'm going to adjust so I'm on my second curve here because my second curve is going to travel faster. I'm going to move Tinkerbell to my leftmost intersection point and then do enter, enter, enter. And you'll know you did it right when it says the word intersection. If it does not say intersection, you're doing it wrong. So we get x equals negative 8.664. And I'm not sure what they're telling you to round to. So in calculus, you have to round to 3 decimal places. I would keep 5 in general, but Pay attention to the rounding. Now we have to do the whole process again. Second, calculate number 5 intersection. And now I'm again moving Tinkerbell. Switch to the straight line because that's faster. Enter, enter, enter. And we get x equals negative 4.497. And second, calculate the intersection of this very last intersection point here. Enter, enter, enter. And we get negative 0.838. And I don't pay attention to rounding. So these are the solutions for x where our two equations are equal. All right, let's look at one more here. So basically, I'm just going to put this in y1 and this one in y2. So 627 times x to the 2.6 power. And here we have 548. This is y is equal to 548. I don't see too much, do I? Why? Because this is y equals 548. My graph stops at 10. So we need to change the window. The viewing window for Casio. So you need to go to viewing window. So go to window, and our y maximum has to be high. It's got to be 548 at least. So I'm going to go to 600. There it is. All right. So now we see, that's the tricky part. You've got to know how to change the window setting on your calculator. So now we can do calculate the intersection. I'm going to move Tinkerbell to my second equation. Now enter, enter, enter. X equals 0.9495, and you're going to have to pay attention to the rounding. All right, ladies and gentlemen, that is good. I know this only had one in, oh, huh. Kind of curious if this has a second intersection point, but I don't know. I don't think so. All right, we're going to leave it at that. Ladies and gentlemen, this is Delta Math 9.6. Have a great day. See you later.